Hi, everybody. I'm David Coleman. I'm Director of Product Marketing here at Extreme Networks. And I'm excited today to talk to you about one of my favorite topics, Wi-Fi design concepts. So first of all, who am I? If you don't know who I am, I'm Director of Product Marketing here at Extreme, but I'm Certified Networking Expert number 4. I've been in the Wi-Fi industry and networking industry for well over 25 years. Follow me on Twitter. There's my Twitter address, at Mr. Multipath. I'm also the co-author of this big fat book that weighs about 30 pounds about Wi-Fi called the Certified Wireless Network Administrator's Study Guide, as well as many other books about Wi-Fi. Although this is a book about certification tests that is vendor neutral, most people that buy it actually buy it for a reference guide, and it is vendor neutral. It's about Wi-Fi. So and one of the topics in this book is Wi-Fi design concepts. So let's go ahead and jump right into it. So when you think about designing for a wireless network, there's really a couple things you think about. You think about coverage, you think about capacity, you think about roaming, you think about airtime consumption. And I cannot emphasize how important it is to design your network and plan a network and not just slap up access points and hope for the best. And the number one thing that comes to mind typically, at least at first, is coverage design, to make sure that your clients have good communications and you've provided proper coverage in your buildings. But you should always think about coverage from the client perspective. Now, a client can understand a signal, believe it or not, all the way down into the billionths of a milliwatt. But you want to make sure that the client has a quality signal. And what is a quality received signal from a client perspective? Always remember, when you're designing for a wireless network, you're designing for the client, the end user. You're not designing for the AP's perspective. And from a client's perspective, you want to pretty much guarantee a received signal of negative 70 dBm or better. That's kind of a common denominator. If you can design for negative 70 dB or better, you're pretty much going to guarantee the high data rates that are available for any particular client. Now, it gets a little trickier with different types of clients, especially when you start talking about voice grade networks. Voice over Wi-Fi is a little bit more intense and it's more susceptible to the harsh RF conditions. So you actually need a better received signal. You need a negative 65 dBm signal when you're designing for a voice grade network. And it even gets better, if a little bit higher, if you're designing for RTLS. Now, one thing you should know that makes this kind of tougher because you're designing from the client's perspective is that not all clients are created equal and they all don't actually perceive an RF signal the same way. They have different levels of received sensitivity. So not only are there clients, older clients that can only transmit at low data rates as opposed to the newer clients that can transmit at higher data rates, all clients have different received sensitivity capabilities. And those received sensitivity capabilities are in turn mapped to data rates. So what does that mean in the real world? What that means is you could have two different clients. You could be holding an iPhone right here and an Android right here, and they might both interpret the received signal at a different level. When you're actually designing, you need to try to design for a lowest common denominator. And so the one that's not the most sensitive, try to design for that in mind. And always remember, there are common denominators as well. So once again, you're trying to design for at least neg 70 dBm or better coverage. And I should also stress that there is importance to have some sort of validation. So once you've come up with a design for coverage for your client receive power capabilities, and once you've actually done the deployment, get out there with some mobile device and do some actual testing and confirm that that's the actual signal strengths you are receiving. Now, there's even more important metrics in my mind in the eyes of the client, and quite frankly, from the access point as well. And to me, the most important one is the signal to noise ratio. The signal to noise ratio is not really a ratio, it's a comparison. It's a comparison of the received signal to what is known as the ambient noise floor. And what creates the noise floor? Well, that's just background noise. That can be anything electromagnetic can create that background noise. It could be, machinery, electrical equipment. It could be computer monitors. It could actually be the sun. So in this example right here, let's just say your noise floor was minus 95 dBm and your received signal was minus 70 dBm. Well, then your signal to noise ratio is simply a comparison. It would be about 25 dB. And that's good. And we'll talk about what a good SNR is. What a bad SNR is the example over on the other side of the slide. And that is your noise floor was about minus 95 dBm, and then your received signal was minus 88. Well, then you're going to have an SNR of about 7 dB. Now, why is that bad? If the received signal starts getting too close to the noise floor, what starts happening is you start getting corrupted packets and frames. And if you start getting corrupted frames, they have to be retransmitted. And if they have to be retransmitted, your overall throughput goes down and the performance of your network goes down. So you want to prevent that. The way to prevent that are these recommendations right here. So these are pretty much some recommendations that are pretty much industry standard for the most part. At the minimum, you want an SNR of 20 dB or better from both the client's perspective and the AP's perspective. If you're going to be voice grade networks, it's got to be 25 dB or better. So that's got pretty pristine RF conditions. And if you're going to start using some of the complex QAM modulation types, it gets even tougher. For 256 QAM, you're going to need a 29 dB or better. And if you're going to use the new 802.11ax 1024 QAM, you need an SNR of about 35 dB or better, which effectively means it's going to have to be in 5 gigahertz, and you're going to have to be very close or right underneath the AP. Now, part of this, too, that what affects your coverage design is also something called dynamic rate switching. Okay. Now, dynamic rate switching is simply this: as client radios move away from an access point, they're going to have a lower received signal, so they will do a downshift to a lower data rate, into a less complex and a simpler form of modulation. As they get closer to an AP, they'll actually upshift. So a couple things about this. Number one, you should understand that APs do this as well. So if a client has moved very, very far away from an access point, the downlink communications from an AP to a client are also going to downshift to lower data rates. So this happens in both directions, uplink and downlink. The downside to dynamic rate switching is that it starts to consume more airtime. The more time, the lower the data rate, the more airtime consumption that happens, and that has a negative impact on your performance. The upside is that make sure you can stay connected to the AP. Now, when you're designing for the network connectivity, you're typically trying to design to connect at that neg 70 dBm or better signal to connect at the client's best capabilities, the data rate of its best capabilities. You really don't want a client downshifting or an AP downshifting. You don't want a client to stay connected to an AP as it wanders very far away. Instead, you want the client to roam. Okay, you want the client to roam to the next AP. And roaming is all about mobility. It was kind of the heart of what Wi-Fi is all about. It gives you that freedom of not having to drag an Ethernet cable everywhere you go. But the one thing that you should understand, and that a lot of people don't understand, is that clients make the roaming decision. And they all have their own metrics and thresholds for that. They decide when to move from one AP to the next. And it's usually based on a combination of signal strength and SNR and some other metrics. But and some vendors publish their roaming thresholds. Apple does, for example, but most do not. Okay. you can actually be holding an iPhone in one hand and an Android in another hand and go walking away from one AP and closer to another, and one might roam before the other, and there's nothing you can really do about that. So there's a couple more things that you should understand when designing for roaming. A lot of times you hear about, oh yeah, when you design for roaming, you got to design for 20% cell overlap or 15% overlap. Well, that's a fallacy because it cannot be measured. First of all, there's no such thing as a nice, beautifully shaped round coverage cell like you see here on the slide. Instead, they look like those kind of convoluted cells that kind of look like big, hideous amoeba shapes, okay? But let's just pretend they were perfectly circular. How would you measure cell overlap? Is it square footage? Is it circumference? Is it the diameter? In reality, cell overlap absolutely cannot be measured, okay? And in reality, cell overlap is simply duplicate primary and secondary coverage, and it's not from the perspective of the AP, it's from the perspective of the client. So a simpler way to put this is when you design for primary and secondary coverage, a client needs to be able to see from whatever AP is connected to, it needs to be able to see at least one or two other APs that are within about a 5 dB range. So if you're designing for neg 65 voice grade coverage, there needs to be at least one or two other APs nearby that it can roam to at about 5 dB below. Other people have different recommendations. They might say primary and secondary coverage should be the same level. So if you're designing for neg 65, there should be another one that's nearby for at least neg 65. Bottom line is there's got to be at least one or two other APs within a close signal range of what you're actually designing for. Now, that being said, another mistake a lot of people make is they put too many APs. So in other words, you have that client connected to the primary AP at neg 65, and it hears 20 other APs between neg 65 and neg 70. That's good. That means probably you have your APs on too high a power. Luckily, a lot of the good prediction modeling apps will help you with your primary and secondary coverage design. Now, one of the things that we provide in Extreme IQ, our cloud management platform, is actual visibility into roaming metrics, and we can actually show you over a historical timeline how long it took a client to roam. You want that roaming time to happen in under 150 milliseconds and really close to under 50 milliseconds. So that time-sensitive applications are not negatively impacted. And we can show you the whole roaming process from layer 2 all the way up to layer 3 in a historical timeline. So that brings me to channel design and channel reuse. And there's, we could do a whole session just on this, but let's hit the high-level concepts. So one of probably the worst way you could design a wireless network is this right here. You put all the channels on the same, all the APs on the same channel. The problem is that RF is a half duplex medium, and at any given time, only one radio can transmit on a single frequency domain, which is just a fancy name for a channel. So in this scenario that you see right here, all those APs actually hear each other. So if one's transmitting, the other three are not. Now, that actually gets called co-channel interference sometimes. But all co-channel interferences is just Wi-Fi working the way it's supposed to work. But unfortunately, with improper design like this, it causes unnecessary medium contention overhead, which is why the primary goal of a channel reuse pattern is to prevent co-channel interference. So in the 2.4 band, everybody should know this. If you don't, you're always going to design using channels 1, 6, and 11 because they're the only 3 channels that don't have overlapping frequency space. And the goal is because there are 3 different channels, they're not interfering with each other and they can all transmit at the same time. So it reduces a channel reuse pattern reduces airtime consumption by isolating the frequency domains. This is once again just a fancy name for a channel. Now, the problem is this. Does RF just stop? Does radio frequency just stop? And the answer is no. It continues to travel. So I guarantee you in the 2.4 gigahertz band, because there's only 3 channels, it is impossible in almost all cases, unless you have lead walls, to prevent co-channel interference in the 2.4 band. I guarantee you 2 APs in the same channel are going to hear each other, and if one's transmitting, the other's transmitting. And unfortunately, it gets even worse because co-channel interference is not static. It's always changing, and the reason being is that client transmissions are the top cause of co-channel interference. So let's just pretend you have 2 APs right there in channel 1, and they don't hear each other and they don't interfere with each other. But a client associated to one of the APs might be transmitting, and it might be heard by another AP and clients on channel 1, and it will affect their basic service set in their RF domain, meaning they have to defer. Clients are mobile, so CCI therefore is not static. And once again, you really can't prevent CCI in a 2.4 band. Now, you can in the 5 gigahertz band with proper design. If you use all the DFS channels, and look at this diagram right here, because there's so many more channels, and you'll note in this diagram right here, the 2 APs on channel 36, they don't repeat until there's a lot of distance between them, a lot of other APs, a lot of other channels, and probably a lot of other walls. This graphic is linear, it's kind of linear viewpoint, but still it points out here just by using the lower uniband and the DFS channels, and you have so many more channels, you can, in most cases, prevent CCI in 5 gigahertz, which is a good reason to use the DFS channels. And one of the things that we have found is that the DFS channels very often are not turned on, and in most cases, unless you have radar interference, we highly recommend that you turn them on so that you can have a better 5 gigahertz channel reuse plan. One of the things we do at an Extreme Cloud IQ, our cloud management platform, is we can actually provide you visibility into DFS. If you don't know what DFS is, that stands for Dynamic Frequency Selection. It's just radar avoidance. So if I'm a AP on channel 100 and I hear radar, the AP and all the associated clients, they have to move to a channel. We absolutely, like every vendor, can do this, but we, in Extreme Cloud IQ, we can actually provide you visibility to this. So if you find a channel that actually is having some problems with radar, it's real simple. You just design around it, and that solves the problem. Another topic that's very popular quite a bit is channel bonding. So, I'm a big believer in most cases of using 20 megahertz channels, but with the advent of 802.11n, that's about 10 years ago, we got the introduction of 40 megahertz channels, and then later on with AC, 80 megahertz and even 160 megahertz channels. So the theory is more frequency space means more subcarriers to modulate data. More modulated data, higher data rates, better throughput. Sounds great, right? So you can see that right here. A 2x2 client AC at 20 megahertz could have a data rate of 150 megabits per second, but with a 40 megahertz channel, it could have double the data rates. Now, in theory, that sounds good, okay? But, 4 channels might not always be the best thing. 40 megahertz channels might not always be the best thing, and because you got to design properly. So at the minimum, you got to have the DFS channels on, all right? So let's just say I use these 8 channels that are non-DFS channels. And I use those 8 20 megahertz channels and bonded them together. That effectively gives me 4 40 megahertz channels. Now, do you see a problem there? You effectively now, you have a 4-channel 40 megahertz plan, which means you're going to have co-channel interference. So the co-channel interference will actually offset any gains that you made by the extra frequency bandwidth. Additionally, every time you do channel bonding, for every 20 megahertz that you bond a channel, it raises the noise floor about 3 dB. So if it raises that noise floor about 3 dB, your SNR gets lower, and that means you also use lower data rates. So should you use 40 megahertz or better? Well, or not? Well, I'm a big believer in 20 megahertz channels in most cases, but 40 megahertz can work if done properly. And so in this chart right here, I'm actually using the DFS channels as well as the lower uniband. And by just using the DFS channels in the lower uniband, that gives me effectively about, I don't know, it looks about 8 or 9, it looks about 12. If you actually use all the unibands and bond them together, you get about 12 or 11 40 megahertz channels for a channel plan. And that can mitigate, or at least help mitigate, code channel interference. So I actually have some rules and suggestions if you're going to use 40 megahertz channels. Number one, you have to have the DFS channels on, period. If you don't have the DFS channels on, don't even attempt to use 40 megahertz. I highly recommend that there's thick walls. If you have an AP in every room and it's drywall, it's probably not going to work. The CCI is going to be too much of a problem. You might not want to use it at multiple floors. And let's always remember that 80 megahertz simply does not scale in the enterprise. It's fine for one AP, but it just doesn't scale in the enterprise. It's not enough frequency space in the 5 gigahertz band. So another discussion that comes up with design a lot is adaptive RF. So every vendor has some sort of adaptive RF protocol. Another term for it is radio resource management. It's the industry standard term for APs automatically changing their power and channel settings. So the argument is, do you use it or not use it, and go with a static or channel and power plan? So we don't have time to debate all the ins and outs or whys and whys not to whether you use adaptive RF. As a matter of fact, most people are going to use it because it's on by default, okay? But don't use it and just think that you can slap up APs anywhere and that the Wi-Fi will just be magic. You still have to do channel design and planning. Think of the protocol as a real-time tool in your toolkit. And in some instances, you might not want to use adaptive RF. You might want to use static channel and power settings, especially in like stadiums, anywhere you're using unidirectional antennas, very, very high density designs, or where Wi-Fi is mission critical. Consider using static channel and power settings. So we've talked a lot about channel. We've talked a lot about coverage. What about capacity? Well, before we talk about capacity, let's just go ahead and put this myth to bed that a lot of people still don't understand. The data rates that are advertised by the marketing departments are not the same as TCP throughput. The medium contention protocol of carrier sense multiple access collision avoidance consumes much of the available bandwidth. So even in today's environments of 802.11n and AC, your aggregate TC3 throughput might be 60 to 70% of the data rate, but that's in pristine RF conditions or laboratory conditions. The medium contention protocol consumes a lot of the bandwidth. So a good rule of thumb is just this. Whatever your advertised data rate is, you can consider that your aggregate throughput is going to be about half of that. Okay, and remember, I also said aggregate because not all devices are created equally, and it's a shared medium, which brings us to the age-old question I've been getting for 20 years, and the question is, how many clients per access point? And the answer is, and has been for 20 years, and will continue to be, is it depends. Now, you see the mad look on this guy's face? The reason he's mad and angry is nobody likes that answer, but it's the correct answer. There's too many variables to answer that question. It depends on what type of applications are being used. It depends on how many clients are, and the one that a lot of people forget about is what type of clients. So let's get into that a little deeper. With applications, not all applications consume the same amount of bandwidth. You know, email and browsing the web's not too bad. It requires per client those numbers that you see right here. Same with printing. Even standard definition video streaming doesn't consume a lot of bandwidth and require a lot of throughput. But then there's a lot of high bandwidth applications these days, especially as we're starting to get into high definition video streaming and other things now like augmented reality and VR. Those things consume a lot of bandwidth. Now, the other thing that a lot of people don't take into mind is that not all clients are created equal. So a lot of legacy clients are only 1 by 1 by 1 clients, meaning they have data rates that are not as high is the more modern clients that are 2 by 2 by 2. Laptops typically have a 3 by 3 by 3 radio and are capable of higher data rates than smartphones and tablets. We live really now in a 2 by 2 by 2 client world, but just understand a lot of the legacy clients, 1 by 1 by 1, are not going to be able to transmit or receive at these very high data rates, meaning if they're 1 by 1 by 1, they're transmitting at lower data rates and they're consuming more airtime, and that affects your overall capacity of how many clients per AP. Now, the good news is there's some there's freeware as well as commercial capacity designers. This is a screen catcher from Ekahau, which is a commercial a design tool that can actually, you can type in a lot of the variables, how many clients, what type of clients, their MIMO capabilities, as well as the applications, and define a very specific area, and that will help you with your capacity planning. So once again, even though you might see on our data sheet that an AP can support, 500 clients, those numbers just aren't realistic in the real world. Okay? Now, we can help you out with that a little bit with Extreme Cloud IQ. With Extreme Cloud IQ, we have something called maximum client capabilities. We look at the probe requests and association requests from client frames that are being sent, and we can actually build a visual view of what the capabilities are of your entire client population. So for future planning of your network, you can actually see how many of your clients are 2 by 2 by 2, or do you have a really high number of 1 by 1 by 1s, and whether they support MIMO or WMM capabilities. So we can show you that, and legacy clients have a way of sticking around too long, and this is quite helpful to help you kind of see how many, especially kind of some of the legacy client capabilities out there that might be dragging down your entire network. So airtime, a big concept in design these days is airtime consumption. And what I mean by that is that due to the half duplex nature of the medium, you want to try to design so that you're cutting down on airtime consumption and that it's fair for everybody. So once again, if you're communicating at very, very low data rates, it's going to drag everybody down. So if you look at this diagram right here, an AP might be sending a downlink framed to a laptop at 150 megabits per second, and you know what? It only takes 50 microseconds to send that frame. But that same size 1500 byte frame sent downlink to a client connected at 6 megabits per second, it might take 1250 microseconds. So that's well over 10, 15 times higher amount of airtime. So if it's taking more airtime to send the same frame, what do you think all the other clients in AP are doing? They're waiting because it's a half duplex medium, and that brings everybody down. So once again, that's why it's a good idea to try to design for high data rate connectivity at neg 70 dBm or higher, and make sure that you have proper roaming design too, so that clients aren't staying connected to an AP and communicating to an AP at really low data rates. Another way to cut down, and this is just a simple one, best practice that most people do right now, is to turn off a lot of the basic rates on your EP radios. And the 2.4 band, I'm going to recommend you use basic rates of 12 megabits per second and disable everything under that. Now, just understand, if you do that, if you have any legacy 802.11b clients, they're not going to be able to connect. But you know what? Who cares? 802.11b is 20-year-old technology, so try your best to get rid of those. Even better, you might want to try to use 24 megabits per second and have everything underneath that disabled. Bottom line is clients will be connecting at a higher data rate, and also all the management traffic goes out at your lowest basic rate, and management traffic consumes quite a bit of bandwidth, and if they're communicating at really low data rates, it's just consuming unnecessary airtime. Same thing for the 5 gigahertz band. Very often you see by default 6 megabits per second is the lowest configured data rate. Don't do that. Use 24. Make that your lowest basic rate. That not only for data communications for clients, but also for the lowest basic rate that management traffic like beacon frames are sent out at. It'll cut down on your airtime consumption. Don't use 18. A lot of drivers on clients don't understand that. Try to use, I would recommend 12 or 24 as your lowest configured basic rate at 5 megabits per second. Another thing to do is, multiple SSIDs are going to consume a lot of overhead. So for every SSID you have that's being transmitted, there's going to be an extra set of beacons, probe responses, and other management frames. So that consumes overhead. So a general rule of thumb is try to have about 3 SSIDs, one for employees, one for guests, and maybe one for like IoT devices or voice devices. It's real simple to achieve this these days. We can do it here at Extreme Networks leveraging what are called user profiles. This can be done either with 802.1x authentication or with our proprietary private pre-shared key authentication and security solution. We can have as many as 63 different user traffic settings assigned to a single SSID. So what that means is you can have one SSID and 63 groups of employees that are all being dumped into 63 different VLANs and 63 different firewall access policies. And that's very, very powerful. That helps you consolidate your SSIDs and cuts down in your airtime consumption. So that's kind of a 101, but a lot of people don't do that. You see this a lot in healthcare a lot. You go into hospitals and they'll have 15 SSIDs for all the different equipment and IoT devices. Consolidate your SSIDs. You'll have a better performing wireless LAN. Another thing, and another thing I want to emphasize too, is all these rules and concepts that I'm talking about, they're not written in stone. There's, sometimes some things that I'm talking about, there might be a better way of doing it. So typically, I'm going to recommend that high power is bad, but in some cases, you might need high power because you might need some ridiculous range in a warehouse for some really old legacy clients. But in most cases, high power is bad. And the reason high power is bad and you don't want to turn your APs up to full power is, number one, you won't meet your capacity needs because you can cover 3 APs will cover a whole building instead of 10, but 3 APs won't meet your capacity needs. Number two, it'll absolutely increase co-channel interference. It causes the hidden node problem. It will absolutely cause roaming and sticky problems where clients aren't roaming properly and they're hanging on to their original AP, which will affect performance. So listen, turn down the power of your access points. In most cases, starting off with them at about a third power or better, you're going to have a better performing wireless LAN. Now, there's always exception to the rules, but for me, this is kind of a 101. And another thing I'm a big believer in using is transmit power control as long as the clients support it. So what an access point that also supports transmit power control can do is it can send a message in an action frame to basically tell the clients to adjust their power to match the AP power and create a balanced link. Now, it's not creating a balanced link for what most people think it's for. It's the main purpose is to do this, it'll basically power down the clients. And who is the number one cause of co-channel interference? Clients. So by powering down the clients to match the AP, effectively what you're doing is reducing co-channel interference caused by clients. Just understand it must be supported by the clients for this to work. Most modern clients are supporting this now, and just understand that some legacy clients might have connectivity issues with transmit power control enabled. Another big thing in design in general is using the environment. Use the environment to help you cut down on airtime consumption and isolate your frequency domains and your channels. Wall attenuation is actually a good thing. It'll help you reduce co-channel interference. It'll help you maximize your channel reuse patterns. And as I mentioned, isolate your contention domain. So using the environment is actually a good thing. Walls help you with these things. And this is why hallways are so bad. Have you ever been in a hotel and the Wi-Fi is just terrible in a hotel? You know why the Wi-Fi is terrible in the hotel? The Wi-Fi is terrible in the hotel because the APs are mounted in the hall. And the reason the APs are mounted in the hall is for aesthetic purposes, because they don't want them in the guest rooms. But the problem is you have, well, just darn cruddy Wi-Fi, because number one, you're not adequately covering the rooms. You need to be putting the APs where the people are. And number two, it causes a co-channel interference nightmare. So, there's nothing wrong with 1 or 2 APs in the hallway, but when you have 10 in the hallway in a linear line, you're asking for nothing but trouble. Which also brings me to, how many APs do you need, really, in typical verticals? Well, it just depends. So you've always heard a lot of times in K through 12 education, you might need 1 AP per room. Been a lot of research done in the United States. Typically, there's about 75 to 80 client devices connecting to an access point per K through 12 classroom. So for capacity purposes alone, and due to Apple and Google initiatives, one-to-one initiatives, 1 AP per classroom is very, very common. And now I'm not saying you have to do this. Maybe 1 AP for every 2 classrooms is fine, depending on your capacity needs. But if you are doing it, it can be done. And if you do need 1 AP per room, based on your capacity needs, you have to have thick walls. If it's going to be drywall, it's not going to work. You need to probably disable 75% of your 2.4 gigahertz radios, because they're all going to interfere with each other. And I would probably recommend not using channel bonding in this case too. And then you can also see I have very low power recommendations. Another way you might be able to attack this, and something that Extreme Networks has been very good at, is dual 5 gigahertz. So Extreme's been doing dual 5 gigahertz for a long time, using what are called software selectable radios, or sometimes they're called software definable radios. And so let's talk about exactly what that means. So, most APs are dual band right now. They have a 5 gigahertz radio and a 2.4 gigahertz radio. But with most extreme APs, our newer models, we have a fixed 5 gigahertz radio. And that fixed 5 gigahertz radio might be transmitting, say, on channel 40. And then we'll have another radio that's a software selectable radio. In this case, it's 2.4 gigahertz and transmitting on channel 6. But based either statically or automatically based on changing RF conditions, that software selectable radio can be turned into a second 5 gigahertz radio. So in this case, now you see 2 5 gigahertz radios from the same AP, one on channel 100 and one on channel 40. Now, I'll take you back to that slide just a minute ago when we were talking about 1 AP for a room, and I said, hey, disable 75% of your 2.4 gigahertz radios so they don't interfere with each other. Well, how about instead, if you could, disabling those, you could turn them into a secondary 5 gigahertz radio. And effectively what you've done is you've doubled your capacity. And that's the beauty of dual 5 gigahertz. And it's been a big winner here at Extreme Networks for a long time, and our customers love it. There are some rules for dual 5 gigahertz. For dual 5 gigahertz, you do need at least 60 to 80 megahertz frequency separation between the 2 channels that are in the same AP. You might want to see if you can pair DFS and non-DFS channels with each other. And channel planning, whether you're doing it manually or you're allowing the RRM protocol to take care of it, gets more complex, because effectively you have 2 layers of 5 gigahertz design, and you need to make sure that the 5 gigahertz channels aren't causing CCI issues. But used effectively, this is a winner, especially, and obviously you got to have the DFS channels as well. Probably going to recommend you not use the 40 megahertz as well with dual 5 gigahertz and stick to 20 megahertz. Always exceptions, though. So another thing that a lot of people just don't think about is using indoors directional antennas. And indoor directional antennas can help in a lot of different verticals in a lot of different ways. So typically most APs are omnidirectional, but directional antennas have very specific purposes. So you can use MIMO patch antennas in a lot of different verticals and scenarios, like libraries, warehouses, retail stores with long aisles of shelves. So if you look at this next diagram right here, This is a warehouse, and in this warehouse, it has long aisles with metal shelves. Now, if you just mounted omnidirectional antennas everywhere, it's not going to be a happy day. So what you want to actually do is use directional antennas for your coverage. And you can actually stagger the antennas on opposite sides of the wall of the warehouse and kind of shoot the coverage down the aisles. This is very, very common in warehouse design. And to take it a step further, you might also still be putting directional antennas kind of at the top of hanging from the ceiling shooting down. So that might be filling in some dead zones that aren't being covered by the directional antennas that are mounted on the side of the wall. So very, very common to use directional antennas in warehouse design, but indoors, but there's a lot more. For example, this is what is called a junction box antenna, and we actually use this a lot. Our professional services team uses this a lot, this junction box MIMO patch antenna. It's used quite a bit in very high density design environments. And what it does, it basically sectorizes your coverage and it isolates your coverage, and it helps reduce co-channel interference, especially if you're deciding to use a 40 megahertz channel reuse pattern. It will help you make 40 megahertz a lot more obtainable, in addition to the other rules that I mentioned. So where is this used? Commonly, as I mentioned, very high density. What I mean by high density is lots of people loaded in one area. So perfect for lecture halls, gymnasiums, libraries, cafeterias, anywhere where you have a lot of people all huddled together. I know that's kind of weird right now with the COVID-19 and everything, but we're going to get back to normal eventually. And if you have high density environments, the directional antennas will help out. They'll definitely help cut down on the CCI and helps you sectorize the coverage. If you're going to be doing this, static channel and power settings. Do not use the RRM protocols when you're doing directional antennas. That's pretty much standard throughout the industry. So you know what the toughest thing to design for? And that's stadium design. And I don't pretend to be an expert on it, but we have experts here at Extreme Networks. So if you are not aware of this, we have Extreme Wi-Fi in a lot of NFL stadiums across the country, and as well as a lot of other sports arenas across the world. And designing for stadiums is tough because now you're talking like 50, 40, 70, 80,000 people. So using directional antennas is obviously going to be part of that. As a matter of fact, we have specially designed APs and antennas specifically for stadiums. Under the seat APs that actually shoot up from under the seat, as well as mounts that mount on rails and poles for shooting directional coverage down on a large group of people in different sections of a stadium. Very tough to design for it. You're actually looking at a software design program called IB Wave. It's probably, in my mind, the best one for stadium design. Give us a call here at Extreme. If you have a stadium at your university or your school or wherever, we'll help you because we have a whole team that does stadium Wi-Fi. You need to have a lot of years of experience, and it's a lot of work and requires a lot of testing. So you've probably heard about Wi-Fi 6. Wi-Fi 6, otherwise known as 802.11ax, is kind of a big change in Wi-Fi. We're not necessarily looking for higher data rates anymore. It's more about improving efficiency using an enhanced technology called multi-user OFDM. It's really, even though it's been around for about a year now, the Wi-Fi 6 clients are really just now starting to flood the marketplace. As more Wi-Fi 6 clients hit the marketplace, I think we're going to start seeing some of those 802.11ax efficiency benefits that will help cut down in airtime consumption. But it really is kind of a paradigm shift in how Wi-Fi operates. plugging a free booklet that I wrote specifically about this topic. It's Wi-Fi 6 for Dummies, and you can download it either using that QR code or from that URL link. I will say this, even though it has dummies in the title, it's pretty extensive review of how 802.11ax and Wi-Fi 6 technology works. So this you might say dummies in the title, but it's not really for dummies. But you'll enjoy the read. So take the time. It's a free download. So that with Wi-Fi 6, I get a lot of questions about, does that change design? How you should think about design. And one is, theoretically, if we have better efficiency, we'll have better performance. And maybe the worry is, are we going to possibly overtake and have a bottleneck in a 1 gig uplink between an AP and an access layer switch? Now, I've been hearing this for years. I heard it with 802.11n, then I heard it with AC. And in reality, except for a few corner cases, 1 gigabit uplinks are more than enough. Now, that being said, I am going to say right now, you probably don't need 2.5 or 5 gigabits uplinks at this moment. But think of it as future-proofing. Number one, as we get more 802.11ax clients it is into the marketplace, it is conceivable that the corner cases of surpassing 1 gig might not be corner cases, and it might become more the norm. I think we're still a few years away from that. Another thing that's going to happen too is we're going to start having more and more radios in access points, and you'll see that in the next slide or two. As we add more and more radios into access points, that means providing more access, and eventually 1 gigabit uplinks might not be enough. That's why any Wi-Fi 6 AP at the minimum has 2.5 gigabit uplink ports on them, or 5 gig uplink ports. If anybody tells you you need a 10 gig uplink between an AP and a switch, that's nonsense. 2.5 or 2.5 or 5 gigabit Ethernet uplinks will be more than enough to future-proof your network for a very long time. The bigger thing you should be worried about in terms of switch design when it comes to Wi-Fi 6 and Wi-Fi in general is your PoE power budget. As I mentioned, APs are putting more radios in them. And it's typically now, if you have 4x4x4 access points that are dual band, it's hard to power them with standard PoE. And you should pretty much think of 802.11at, otherwise known as PoE plus, to be a requirement these days to power anything that is 4x4 or bigger. You're going to need about that 25 watts of power. There are some exceptions. If you have smaller APs that are the 2x2x2, you can still power those with 802.3 AF and 15 watts. But pretty much rule of thumb, PoE plus. And you're going to need PoE plus for anything 4x4 or bigger moving forward. And as we add more radios in it, that's going to be a challenge. We want to try to keep it to that level of power. I think the bigger issue I'm worried about is people doing one-to-one replacements. And when they do one-to-one replacements with older technologies, they might not be thinking about their power budget. And if they don't think about their power budget, all of a sudden they're exceeding their power budget, and then you start getting APs randomly rebooting. So that's your first sign that you haven't done proper power budgeting. So PoE power budgeting for switching, whether it's Wi-Fi 6 technology or Wi-Fi or any technology, it's critical. And I will say this, that is one of the cool things about Extreme Cloud IQ, is not only can we give you visibility in your Wi-Fi network, but we can also give you visibility to all the Extreme switches, including their power budget. So as we wrap this up, you've probably heard a little bit about 6 gigahertz. And yes, the FCC in the United States has recently approved the use of the 6 gigahertz frequency band for unlicensed communications, including Wi-Fi. So starting in 2021, guess what? There's going to be Wi-Fi access points and clients. We'll be able to transmit in this whole new band. And effectively, this is double the frequency space that we had of 5 gigahertz and 2.4 gigahertz combined. Now, this could be a whole topic in and of itself. I'll just say this. You'll see Wi-Fi 6 APs that operate in the 6 gigahertz band coming in 2021. It'll take a long time for the clients to follow. And you should also keep in mind that this is not backward compatible with 5 gigahertz or 2.4. So all those legacy clients that are still out there, they're not going to magically work on this band. So please understand that. The potential for this is fantastic. I mean, look at all those new channels. And I also think this will make 40 megahertz channels pretty much a rule of thumb in a lot of cases now, simply because we have all this frequency space. And you will see access points with a lot of different form factors, some with 5 and 6, 6 and 5, 6.5, 2.4, some with software selectable. So it is very exciting. And this will be pure 802.11ax technology coming your way too. So some of the protection mechanisms that you needed for backwards compatibility won't be required. So you will also be able to take better advantage of the multi-user technologies like OFDMA in all this great frequency band. So this is very exciting stuff, and it will bring a whole new caveat into design for wireless LANs. You'll have to be thinking about not just 2.4 coverage and 5 coverage, but you'll also have to be thinking about 6 gigahertz coverage. 6 gigahertz will also be great for mesh backhaul as well between APs. So you'll be hearing lots about 6 gigahertz in the coming years. But in the meantime, I hope you have enjoyed this presentation. Once again, my name is David Coleman at Extreme Networks. Thanks very much, and we hope you'll tune in again.